It is recording, okay? So be silent. So today we'll start module 2. Module 2, that is oscillation. Oscillation. Okay? So in the oscillation, first is the periodic motion. What is periodic motion? Periodic motion. Hello? What is periodic motion? Anyone? Hello? Anyone? Periodic motion? Everyone will go. Follow. What is periodic motion? What is the definition? Time taken? What is periodic motion? Okay, periodic motion. The motion which repeats itself. The motion which repeats itself in equal interval of time. The motion which repeats itself in equal interval of time, then that is called the periodic motion. Okay? So when a particle moving in a circle with a uniform angular velocity, then that is called periodic motion. Okay? Also, if a particle is moving in back and forth in equal interval of time, then that is also called periodic motion. So, in periodic motion, there are two types of motion. One is called circular motion and another is the back and forth motion. Okay? Second one, oscillatory or vibratory motion. Oscillatory or vibratory motion. Okay? What is that? If a particle in periodic motion, moves back and forth, if a particle in periodic motion moves back and forth, that means when we start from O, then it goes in this direction, after then it coming in this direction, then goes in this direction, then goes in this direction. Then that is also called the oscillatory motion. But it is like a periodic motion, but it is a back and forth motion. So this is the circular motion. This is called the oscillatory motion. Okay. So if a particle in periodic motion moves back and forth over the same path, then the motion is called oscillatory or vibratory motion. Then the motion is called oscillatory or vibratory motion. Okay? Now we go to the simple harmonic motion. Okay, what is simple harmonic motion then? Simple harmonic motion, SHM. What is the definition of simple harmonic motion? When a particle under oscillatory motion, when a particle under oscillatory motion, that means the particle starts from O, goes to B. Okay. After then, from here it again comes here, and it goes up to this one. That is called the simple harmonic motion. Okay. But in simple harmonic motion, the restoring force is proportional to the displacement. Okay, in simple harmonic motion, the restoring force is proportional to displacement and always directed towards the mean position. Okay, always directed towards the mean position. That is your mean position. So when the particle comes from here to here, then what happens? The restoring force is proportional to x. If the displacement is x. But the force is along this direction. Okay, so what happens? At a certain point the force becomes 0, after then it comes in this direction again. Okay? SHM is an oscillatory periodic motion. SHM is an oscillatory periodic motion. So it is oscillatory as well as periodic motion, okay, such that the restoring force is proportional to displacement of the particle. Displacement of the particle from a fixed point. Displacement of the particle from a fixed point O. From a fixed point. In its path. From a fixed point in its path. And always directed towards the from a fixed point in its path and always directed towards a mean position. Always directed towards a mean position. Mean position means this one O. Okay. Now what is the restoring force? So how we get the simple harmonic motion? Now when a particle moves in a circular path with an angular velocity omega naught. Okay. The particle starts from here. Then the foot of the particle. Foot of the particle means if we take the projection of the particle, then what happens? It starts from here. So the foot is also here. Okay. Now, when the particle comes here, then what happens? What is the foot? This is the foot down. So the foot of the particle comes here. So as the particle comes here, then it is here. Okay. In this way, when the particle comes here, the foot is at 0. So if we draw the graph like this is the time and this is the displacement of the foot of the particle, not the particle. Okay, displacement of the foot of the particle. So at the time 0, it starts from here. So when the particle is here, then the displacement now decreases. And when the particle is there, then the displacement is 0. It is 0. After that, when the particle is there, the foot is there, that means it goes down, negative direction. Okay. And when the particle is there, it will again come to the maximum position here. The foot. Again, when the particle comes here, it goes 0, that means again it decreases, and when the particle is 0, it is 0 here again. Okay. Then when the particle comes here, it is like this. So we get a cost curve. Okay. So we get a cost curve. So that is the simple harmonic motion. So what is the simple harmonic motion? Simple harmonic motion is the foot of the path. Okay. Foot of the particle. The motion of the foot of the particle is called the simple harmonic motion when the particle is moving in a circular orbit. Okay? With a angular velocity omega 0. So that is the simple harmonic motion. But if the particles now if the particles start from here, if the particles start from here, then the foot is here. If the particles start from here, then the foot is there. That means start from 0 now. Then when it comes here, then it is negative. So it goes in this direction first. Okay? Or if the particle goes in this direction, then it is maximum here when it comes here. Okay? After then, again it is decreases when it comes here. How it is moving in this direction. Okay? After then, when it comes here, it is negative maximum. And again when it comes here, it is 0. So this is the sine curve. So the simple harmonic motion may be sine or cosine, anything. Okay? So this is the simple harmonic motion. Now, the differential equation of simple harmonic motion. The differential equation of simple harmonic motion. Differential equation of simple harmonic motion. If a particle of mass m, small m, is under simple harmonic motion, differential equation of SHM. If a particle of mass m under SHM and at a time t, the displacement of the particle from the mean position is x, and at a time t, the displacement of the particle is x. Okay. Then the restoring force at the point P. Then the restoring force at the point P what is the restoring force? Newtonian force. What is the Newtonian force? At x. M d2 dx2 dt2 mass into acceleration. So when the particle is at x, what is the acceleration? d2x dt2. So mass into acceleration is the force. This is called the restoring force. So when the particle is there, then the restoring force is in the direction, and that is m d2x dt2. Okay? And as per the definition, the restoring force, as per the definition, restoring force is m d2x dt2. The restoring force at the point P is m d2x dt2. As per definition of SHM, the restoring force is proportional to displacement. Therefore, m dq dt2 proportional to minus x. Why minus? Because it is directed along the mean position, always opposite to the restoring force. Therefore, the restoring force m dq dt2 proportional to minus x. Now we have put a proportional constant. What is that? Stable. Or m dqx dt2 equals to minus c into x. C into x. Where c is the proportionality constant. Where c is the proportionality constant, full stop, it is defined as restoring force per unit displacement. It is defined as restoring force per unit displacement. Okay, restoring force per unit displacement. Why? Now from there we can get c equals to minus m dq dt2 by x. What is m dq dt2? M dq dt2 is the restoring force. So c equals to restoring force per unit displacement. Okay, so this is the restoring force per unit displacement. Now, if we take the cx in the left hand side, take this one in the left hand side, or m d2x dt2 plus cx equals to 0. Okay. Or d2x dt2 plus c by m x equals to 0. C by m x equals to 0. Follow? Any problem? Okay. Now we put c by m equals to omega 0. Okay. पहला हाँ ये नहीं ये यहाँ से है देखो फिर then d2x dt2 plus c by m into x equals to 0. Now this is the constant. C is the constant. M is the mass of the particle, which is also constant. So we take this constant as our d2x dt2 plus omega naught square x equals to 0. Omega naught square x equals to 0. Where omega naught equals to root over c by m. Omega naught square is c by m. So omega naught equals to root over c by m is known as angular frequency. Okay, this is the angular frequency in which the particle is moving. Okay, angular frequency. So now this is the second order differential equation. can solve it. How we solve it? Using the trial solution, x equals to e to the power alpha t. Okay. So in your syllabus there is no solution, only you must write on the solution only. Last one. The solution of this equation, the solution of equation 1, the solution of equation 1. This is the differential equation. Equation 1 this is the differential equation of simple harmonic motion. This is the differential equation of simple harmonic motion. The solution of equation 1. The solution of equation 1 is x equals to a sin omega naught t plus delta. This is the solution of equation 1. X equals to a sin omega naught t plus delta. Where A is the amplitude, where A is the amplitude of the oscillation, omega naught is the angular frequency, omega naught is the angular frequency, and delta is the phase difference. Delta is the phase difference. PHAC. What is phase difference? If the particle does not start from here and if it starts from here, then this angle is called the delta. It is not sure that the particle starts from the mean position. It may start from here. Then that is called the delta. And what is omega naught t? Omega naught t is the angle, this one. Displacement, angular displacement. What is angular displacement? Angular velocity into time. That is omega naught into t. So that is omega naught into t is the angle and also delta is the angle. So it is sin omega naught plus delta. So this is the simple harmonic motion. Velocity of the particle under SHM. Velocity of the particle. Velocity of the particle under SHM. Velocity of the particle under SHM. What is equation 2? Equation 2 is the equation of the particle under SHM. Okay, or the displacement of the particle of the particle under SHM at time t. Now that is the x. X is the what is x? X is the displacement of the particle at time t. Okay, so the velocity. So we know the velocity v equals to dx dt. We know the velocity v equals to dx dt. So this is the x. This is equals to ddt of a sin omega naught t cos delta. Now find out the differentiation. A sin omega naught t plus delta. Now differentiation करो. So this is equals to omega naught cos omega naught t plus delta. Okay, so this is equals to a omega naught root over 1 minus sin square omega naught t cos delta. Cos theta equals to root over 1 minus sin square theta. Okay, so this is equals to a omega naught root over 1 minus sin square theta x by a. From equation 2 we get sin omega naught plus delta equals to x by a. So we can write it here x square by a square. So this is equals to omega naught root over a square minus x square. So v equals to omega naught or v equals to here we must put plus minus. Okay, cos theta equals to plus minus over 1 minus sin square theta. Why it is plus minus? It goes, if it goes in the right hand direction, then it is plus, and if it goes in the left hand direction, it is minus. Okay, so I put plus minus. And you can see that A is the maximum amplitude, there is maximum displacement. A is the maximum displacement. So when x equals to 0, then v equals to be a omega naught. So when x equals to 0, then v equals to a omega naught. That is the maximum velocity. X equals to 0 means at the mean position. At the mean position, the velocity is maximum. Here x equals to 0. Okay. So at mean position here, the velocity is maximum. Therefore, v max equals to plus minus a omega. At x equals to 0, velocity is maximum, and it is plus minus a omega naught. Sorry, a omega naught. And where it is minimum velocity? At x equals to a. At x equals to 0. At x equals to a, this is v minimum. V minimum equals to 0. So here at x equals to a, v equals to 0. Okay, and here v equals to plus minus a omega naught. Maximum. Now we find out the acceleration. Terms of the acceleration of a particle under SHM. Acceleration of a particle under SHM. Acceleration of the particle under SHM. The acceleration of the particle is F equals to dv dt. And we don't take A. Why? Because A is the amplitude. So no F here. F equals to dv dt. So this is equals to ddt of A omega naught cos omega naught t plus delta. This one. This one. A omega naught cos omega naught t plus delta. So this is equals to
minus A omega naught square sine
A omega naught square minus A omega naught square sine omega naught t plus delta. Minus A omega naught square sine omega naught t plus delta. So this is equals to minus A omega naught square. This is x by A. This is x by A. So A cancel. This is minus omega naught square x. This is the acceleration of the particle under SHM with the minus sign. Why it is minus? Why the acceleration is minus? Because the acceleration force is created in mean position. That means acceleration also created in the mean position. So velocity goes in this direction, but acceleration is in this direction. It is only possible in case of SHM. Okay? The acceleration is in the opposite direction of velocity. It is only possible in case of SHM. Okay? That's why we want. Now, when S is maximum, now when x equals to A, but at the time v equals to 0. So when the velocity is 0, then acceleration is maximum, but it is directed along this direction. তাহলে তো v0 হবে না, তো কখনোই v0 হবে না, ইনফিনিটি তে চলে যাবে। ওকে, so at x equals to A, it is maximum f max equals to minus omega naught square A, but the velocity is 0. And here at the mean position, at x equals to 0, f equals to 0, that is the minimum. So at the mean position, the acceleration is 0, but velocity is maximum. Okay. But at the acceleration 0, velocity is maximum. So it is possible only in case of SHM, where there is no acceleration but velocity is maximum. Okay. So this is the what? Simple harmonic motion. Not impulsive, negative. Minus the displacement force is minus of displacement is of plus. Minus of displacement of zero. What? Most of minus of okay. So this is the simple harmonic motion. Okay, silent. Last three bench. So this is the end of the simple harmonic motion. There is nothing in your syllabus for simple harmonic motion. Then we start damped vibration. Okay, what is damped vibration? The simple harmonic motion is the ideal concept. Sorry. Now, if we draw the simple harmonic motion, displacement x and in this direction t, then we get this is the simple harmonic motion. Why? Because A, then the amplitude is always constant as the time passes. In case of simple harmonic motion, the amplitude is always constant as the time passes. But it is not possible in reality. Simple harmonic, what is the example? Simple pendulum. But is it possible that simple pendulum is oscillating for an infinity time? No. Why? Because the amplitude decreases. For every oscillation, amplitude decreases and ultimately stops. That is called the SHA. That is called the damped vibration, where the amplitude decreases and ultimately it stops. So all the motion are damped vibration, not simple harmonic motion. Okay, simple harmonic motion is the ideal concept. We have to know the damped vibration. Okay, so damped vibration. Damped. That means when the amplitude decreases. Why the amplitude decreases? Because there are so many frictional forces, internal and external. So when there is a pendulum, when the pendulum is oscillating, then ideally there is no mass of the pendulum, but it has a volume. Okay, or a point mass where the volume is very small. But you know that in a pendulum, there is a volume also. So if there is a volume, then there is friction in the air, which decreases the amplitude. Okay. Also here, there is, somewhere it is called angle. There is also a frictional force, due to which again the amplitude decreases. Okay, and also the thread. For the thread, there is also the amplitude decreases. Okay, so these are the frictional force that is called the damp, that will which resist the simple harmonic motion. Okay, these forces resist the simple harmonic motion. This is called the damped force. These are called the damped force. Due to the damped force, what's happened? The amplitude of the vibration decreases, and ultimately stops. That is known as the damped vibration. Okay. When a particle vibrates, when a particle vibrates, it faces a number of frictional forces. It faces a number of frictional forces. Frictional forces within bracket level, external or internal. External means the weight of the mass of the bulb, and external means air. So stuff. These forces decrease the vibration. These forces decrease the amplitude of vibration. These forces decrease the amplitude of vibration. With time. motion of the particle ultimately stop. And the motion of the particle ultimately stop. Such vibration of decaying amplitude, such vibration of decaying amplitude is called, such vibration of decaying amplitude is called damped vibration. Okay, so this is the damped vibration. Now, if we draw, this is the displacement x, time t. This is the undamped motion. Undamped motion. Okay? Undamped motion. And what is the damped motion? This is x, this is time. This is the damped vibration. This is the damped vibration. Okay, here you can see that here the amplitude is constant. But here the amplitude decreases and ultimately it stops. So this is the undamped, this is the damped. So we have put this one. In the next class, we will find out the differential equation of damped vibration and also we will solve it. Okay, there is a solution. So we must solve the differential equation of damped vibration. Okay, thank you everyone. Now we will take the